So, hello everybody. Let us continue where we took off. So, basically what we already know is how to train your artificial neural network in all the details, how to calculate gradient, how backpropagation algorithm works. And what I wanted to discuss today is that the neural networks is not the only algorithm you can use in machine learning. Yes, so we'll cover some additional algorithms and how exactly can we use them in Python environment. But before we begin, let us briefly check how exactly you can, in more, let's say, a working environment, in more like realistic world, create neural networks using existing libraries in Python, such as Keras, TensorFlow, and how simple it is to compare with the practical exercise we had where we were actually programming this neural network ourselves. So here in the Ortus system I have provided you some collab codes, yes, for which you can open it and study documents. So let's see, for example, how we can make exactly the same neural network as we did in the practical exercise number 4 in much simpler way. So first of all, we import whatever necessary stuff we do. Then we still need to split dataset and convert the labels into categories, so nothing new happens here. What is new is here that we specify algorithm which we are going to use. In this particular case, we are going to use a neural network, so we import a model called sequential. Yes, that means that you specify the neural network structure as a sequence of layers, and that is it. Specifically, we only are going to use a layer of type dense, that is the only one we will use here, and we also need to use some algorithm instead of minimize functions. So, for example, stochastic gradient descent or RMS graph. And we will evaluate accuracy then. So then you import the dataset as we did before, nothing new here. Then you specify parameters of your neural network. Again, nothing new comes here. You split the dataset exactly like we did. You convert data into categories. Well, again, nothing new here. And here comes how we create a neural network. So the model 1 is this artificial neural network of the type sequential, and here you can see that we add layers to this model 1. So in a sense, here we have same structure of input layer, hidden layer, and output layer. And you specify these parameters as the size of this layer and the type of the activation function you want to use, for example, sigmoid. And for the first layer, you also have to specify how many inputs does your neural network has. And then you can add as many layers as you like. So, for example, I can copy this, copy this line and say I need one more layer, one more layer, one more layer, and so on. So this is much simpler than programming it yourself, of course, yes? And only after that you simply specify whatever parameters of optimization you want, such as learning rate, number of iterations, and all that stuff. You choose the algorithm, so here we use stochastic gradient algorithm, and then you say that you want to compile this model by using specific cost function, categorical cross entropy, specific optimizer for metric called accuracy, and train this neural network by using a method fit. You will see today that exactly the same structure is for any other algorithm we'll cover today, support vector machine or decision tree or whatever else. You simply feed this, you simply create some model, for example here, and then you feed the data to this model. After it has been trained, you can use it to predict the data set points and evaluate accuracy. And that is it. Yes, so basically these lines cover everything we do in the practical exercise number 4. And here you can focus more maybe not on how to calculate backpropagation or how to implement this function, will it work correctly, but more on the architecture, like what exactly activation functions do you want to use. You can use, let's say, ReLU instead here, or softmax at the output, yes. You can decide that you want to have more layers. Maybe you want to use some other kinds of layers. Maybe you want to use another type of optimizer. So you can play around with these parameters easily without having to worry how to encode them. And that's exactly the practical exercise number, which is 4, yes, in our case, which is in a sense like a bonus practical exercise, which I will kindly ask you to work on top yourself. Yes, we will not do it in class because, well, it's very similar to what you will do next, and accordingly here you basically play around with different configurations of neural networks, which is easier. And again, you have this document available which can help you to finish that practical exercise also. So that one will be for you to work on yourself. Next week we will start working on some unsupervised methods when you do not provide the outputs and do not say what is your y labels and want to still do some algorithm, yes? So this is just to show you that using this Keras, yes, and TensorFlow, which is used for Keras as well, you can simply specify this neural network in a matter of few lines of code, and then, if necessary, you can change it and run again, change it and run again, to find the best architecture, the best number of layers, the best number of hidden neurons, etc., etc. So it is actually, to use in real world, very simple. And all our future practical exercises are going to be more like this, instead of what we had previously, where you had to, you know, program the gradient descent method yourself, where you had to program backpropagation yourself. That was the most difficult part of the course, when we actually delved into details, into theory, and learned how this exactly works. Now, from this point, yes, we will study more how we can use it and what is our, well, limitation here, what we can do and what we cannot do, yes, without worrying how exactly it works inside, because we already know that. So, with that in mind, let us cover some other algorithms in addition to, well, regression, which we covered already, and neural networks, yes. So we'll speak today about some decision trees, random forest algorithm, and support vector machines, which are also quite popular and sometimes used when you don't necessarily need neural networks. Or, for example, neural networks has this specific disadvantage that if your data contains some noise, then it is not so good to use. Yes, and other algorithms, such as random forest, for example, may be better solution for you. So let's cover these algorithms, how do they work, and also we'll cover some additional metrics, because we already know accuracy, but as you will see, accuracy is not always the best way to tell if your model works well or not, so we'll cover some additional metrics as well. So let's start with decision trees. You can think of this decision tree as a certain roadmap, yes, when you split your input data into some categories based on, well, whatever outputs can be. Yes, so for example, here you can see you can have shape of rectangle or a shape of a triangle, yes, but they can also be rotated somewhat. So basically there are two types of the shape, but there are variations for this exact shape. So your rectangle can be either this straight or this rotated, yes. Same goes for the triangle, it can be pointing up or pointing down, yes, either straight or rotated. So basically you make some kind of a tree in the process, and by the way, this is also a very good algorithm which can help you to process your data, yes, because, well, as I was saying in our practical exercises, I have prepared the data set for you, I removed whatever empty spaces the tables had, and actually this can work with empty spaces as well. So what it does, it makes the problem of telling if the shape is rotated or straight, triangle or square more simple by splitting it into consecutive smaller problems. Like first you try to decide, is it rectangle or triangle? And only then you see if it is rotated or not. You don't do them at the same time, yes? And accordingly, a final decision is made based on this path on this tree. So what we have here as a structure is then like we have certain root, starting point from which this tree grows, and certain conditions as internal node when you decide, for example, if this object is I don't know, round, if it's square, if it's red color, if it's blue color, yes, etc., etc. Different kind of conditions which can branch. So it doesn't necessarily has to provide answers right away. You can have next condition after this condition. As you can see, this goes into this and branches further, and you can have this, well, layered structure branching as many layers as necessary. So again, let's say here we have root, then it splits into, let's say, 3 conditions: condition 1, condition 2, condition 3. Then condition 1 can again split further in condition 4 and 5. This can be either producing some answer or check for condition 6. This, for example, provides 2 possible answers, answer or answer, yes? So you can nest this structure as deep as necessary, and this is in fact one of the parameters which you specify in the Colab, for example, or any other Python code, as this depth of the tree. How many layers of this tree is the limit for your problem. So this is something you can choose, or it can go default until it runs out of the options, yes, by studying your data. Now, some specific advantages here include, of course, very clear visualization. In fact, you can make this decision tree just to understand better what is exactly your data and how it can change. Also, it doesn't need any kind of scaling, yes, so we don't do scaling for this, and it's not a problem if your data is linear or not, which was for example, linear regression or some other algorithms, as you will see, such as support vector machine or something else, yes. Now, if you have certain points that stand out of the other points, like some anomaly in your data set or missing values or whatever else, it can handle it automatically, yes. And it also doesn't require you to make any kind of assumption what kind of data you have. Is it having a, let's say, normal distribution? Is it having some other distribution? So nothing of that really matters. But there are, of course, also some disadvantages, mainly because it can be unstable, yes, so sometimes it works correctly, sometimes it does not, especially if your data has certain noise to it. Now, it's also, as you imagine, constructing this kind of a structure for a lot of data is consuming, computationally wise, so it's well suited for a small amount of data, not exactly for a large amount of data. Now, there is also a problem of a data balance, of which we'll speak a little bit further, yes, when you have, let's say, 100 cases of class 1 and only 3 to 4 class 2 dataset points, yes. Now, if your dataset is quite large, then you have high complexity for computation and also high risk of overfitting the data. Now, if we switch to how exactly it's implemented in the Python environment, yes, here you can see that for decision tree you create an object called decision tree classifier, which you import from sklearn library. Then you use the same method fit as we did for neural network. Then you use the same method predict as we also used for neural network. So in a sense, what changed is that now your model here is decision tree classifier instead of this sequential neural network, yes? And then you use fit and predict. So it's as simple as that to use it. And you evaluate some accuracy. So let's say here I actually loaded this data set of handwritten images, yes? And you can see that decision tree in this case provides the accuracy of 77%. Now, our neural network we had before was providing the accuracy in this particular example 84% for stochastic gradient algorithm method. For others, and with different parameters, different learning rate, it might be better. But still we can see that neural network here works actually better than the decision tree in this particular case, yes? So, not very difficult to program it. You process data exactly same as before, load, split, and convert to categories. So, nothing new here. And we'll cover other algorithms as well as we go through them. Now, what is the most difficult part about this algorithm is to correctly choose your root at this point, because depending on your choice, your tree is going to be different. So let's see this kind of example where you have some data set with person's age, his income level, if he's a student, and his credit rating, yes? And what you want to try to predict, is this person going to buy a computer in your shop or not, yes? Now you can choose as the root, as the starting point for your decision tree, for example, the age, yes, based on the age, and after the age it's going to branch. Or as the main starting point, you can also choose his income. So that is another alternative. And depending on which you choose, the accuracy of your model might be different. Yes. So the choice of this root node is, well, affecting quite a lot. Now, of course, we are not going to blindly guess which we should use or should not use. So, for example, for this case, yes, you calculate some statistics, and based on these statistics you decide which you want to choose as the starting point. So you calculate certain entropy. Entropy, as you already know, we calculated this as for cost function for logistic regression. Yes, so you have probability multiplied by log 2 of the probability. That is called entropy in information theory. In telecom it's quite important parameters, but here we use it as kind of certain metric, yes, to decide which of these columns is going to be your base root column. And we do it as follows. So for example, we check for the age for each possible criterion, less or equal 30, 31 to 40, more than 40, which are 3 possible ranges. Yes, how many data points do you have as matching this criteria and not matching? Yes, so for example, not more than 30 years, we have 2 people in this data set, and others are not matching this criteria. Same way, we go for the next interval from 31 to 40, we have 5 people matching this criteria, and 0 not matching, yes? Which is, well, for some example, yes? Not exactly sure if it's accurately this case. 1, 2, 3, 4, 5, yes, 5 cases. Well, these are not exactly tied to this dataset because, well, it's going to continue, yes? So this is just some demonstration, yes? Some numbers, not particularly for this dataset. And then for the last category, more than 30, yes, 2 and no 2. Same goes for the income column, yes, for each category, high, medium and low, you calculate some statistics. Yes, same goes for student, like 6 students, not student 1, and for no, opposite, yes, gradient rating, and so on and so on. And afterwards, you calculate this as a probability, yes. So, for example, let's see this one. That is for the age column. You can see here yes is 2, yes is 5, and yes is 2. Yes, so accordingly we have in our data set 9 people of matching the age criteria. So that means that you have actually more to this table, and here you can see only first 5 cases. Yes, so accordingly these go further. So that brings you here 9. Yes. Out of this first column age 2, 5 and 2. That is 9. Now total is 14, and accordingly no case is the complementary. Yes, these 3 plus these 2. So this is probability of yes, and this is probability of no, and you calculate this entropy as the summation of these 2 probabilities, like entropy of, let's say, so where it is, sorry, entropy of age as minus probability of yes multiplied by log 2 of probability of yes minus probability of no multiplied by log 2 of probability of no. So as you can see, you cover all the possible outcomes, which in our case is binary, yes or no only. And then you get the number, for example, like this, yes, for this particular example. Now you do this procedure for each of these columns and calculate their entropy, and you will choose as the main point for your decision tree whichever is smaller, the minimum for all of these columns. So in this example, I have created like H has the minimum entropy, so that means the H is going to be your root of this decision tree, and everything will branch based on the H. Yes, so you will have then as a starting point this H, which can then go in 3 different conditions. This condition, this condition, or this condition. Now any other column, income, student, etc., can happen in all of these 3 cases. So you then are going, say, for the income, cover it again in 3 cases: high, medium, and low. High, medium, and low. High, medium, and low. Maybe it's possible that, for example, at the age less than 30, there will be no people with high income. So that will be this way only 2 possible branches. It's completely possible that there will be simply no data set points having, let's say, high, saying high income in this category, age category. So medium or low only. So they don't necessarily have to be present in all the cases. Yes, you only have decision tree. Whatever you have, you split that into categories further, as it can be split. Yes, so that's completely normal. But the idea how to choose the root is quite simple. You calculate the entropy for each column based on statistics, how many yes and how many no you have, and choose whichever is the minimum as the basically how it says root. Yes, so you can also calculate the gain of information. That is why we choose this H entropy as the maximum, because the gain of the information is H minus this whole entropy. Yes, and the less is this probability, yes, the more you will have as the well, remaining. Yes, so basically you take this 0.94 minus this H entropy, and you get this number. And this is amount of how informative is that column for you. And obviously, as the most important starting point choice, we want to have the most informative column. That's why we choose the minimum entropy, actually. Yes. There are also other algorithms as to decide which is starting point, such as CART algorithm, C4.5, Gini impurity, yes. So these are all the ways to decide whichever is your starting point. Let's see some other example. Let's say you have some computer network traffic which you try to analyze and say if it is normal traffic or it is a cyber attack of certain type. Yes. Now you have decided or basically calculated some entropies, and it turned out that the flow rate is the most informative parameter of them all. But there is also duration parameter, how long is connection, how fast is data transfer, and what is the size of the transfer data. Yes, so you have 3 parameters here as inputs. So first is data rate, so how fast is your connection. Second is duration, how long is this connection. And the large is the size of transmitted data. Yes, and you decide to make a decision tree based on this structure and the data set you have. Yes, you have some data set which contains correct answers where was it attacked and when it wasn't. And you can see, for example, this kind of a structure that if you have a low speed data connection
but this is a long connection, so they're happening something for a long time with very low speed, then it is probably an attack, yes? Whether if it's just a slow connection and short durations, this might be some messenger, some email checks, regular, some update checks, and something like that, which is a normal traffic. Again, based on the data set you have, you see that if your flow rate is somewhat medium, not small, not high, yes, then this is also a probable attack. And for the flow rate which is high, if you have high data transmission rate and set large volumes of data, then this might be some kind of DDoS attack or something else, yes. If it's a small amount of data, then it's probably a normal traffic. So this is in fact actual research, which you can see on this ResearchGate website if you're interested to know more details about this particular decision tree. But I have included this just to show you as an example. Now, let's go to the next algorithm, which actually relies on the decision tree algorithm, which is called a random forest. So, as you know, a regular forest consists of trees, just like the same way, a random forest will consist of decision trees. Yes? So, you will have multiple decision trees, and in a sense, this is a voting algorithm which is making a final decision based on multiple algorithms. So this you can think as some kind of election process that where you have, let's say, 4 algorithms. Each of them makes some kind of prediction, and then in the end you make voting. Like the first algorithm, for example, says in this particular case, I don't know what kind of problem, but maybe yes. The second algorithm says yes. The third algorithm says no, and the fourth algorithm says yes. So the final outcome is going to be then yes, based on majority of the votes. Now this idea is very nice because you can this way focus on simpler models. You can use neural networks here as well. It's not necessarily has to be decision trees. You can use other algorithms too. But the most natural way is to use some kind of decision trees and then make a final prediction based on the majority of the votes. And each of these decision trees themselves is much less powerful model. So you have, instead of building one very complex and very accurate model, you can make 4 more simpler models and then basically use their output by simple voting. Now, let's say if you want to use a classification problem, if you want to use regression problem, like where you want to predict some price or Bitcoin currency exchange rate or something like that, then instead of voting, you will simply calculate the average, the statistical mean of all the predictions. Now here, for example, you can see that our random forest algorithm is used to try to predict different kinds of fruits, and it consists of 3 decision trees. Tree 1, tree 2, and tree, well, not exactly 3. In this picture you can see 3, but actually there can be more than that, as you can see, 3n, let's say. Yes? So now you can see that tree 1 says that the fruit being studied goes through this path along the tree 1, and outcome is that it's apple, yes, red apple actually. Now, the second algorithm is different decision tree, but it also produces the output that it's apple. And the last one makes mistake, yes, predicting that it's actually banana. And then the final vote is simply counting how many occurrences for each class have happened. Now, if again you want to make some kind of cost predictions, some kind of, I don't know, exchange rate prediction, maybe temperature prediction or stuff like so, then you will use regression problem, and instead of simply voting here, you will calculate the average of all the outputs. Now, again, there are always advantages and disadvantages to all of this algorithm, and unlike the decision trees of which our random forest consists, decision trees could be unstable. Now, the random forest, although it consists of decision trees which can be unstable, the algorithm itself, random forest, cannot be unstable. Yes, so it is actually highly stable algorithm. It also does not need to split the data set into training and testing parts, and can be actually, which is very important, well parallelized. Yes, so as you know, we live in era of GPUs, graphical processing units, which can calculate very simple operations, but in large bulks, so in parallel. And having multiple decision trees allows you to have multiprocessor system, and each processor of your system is going to work on its own decision tree, and accordingly provide you result faster in parallel. Now, the main trick here, how do you make these decision trees different, is that actually you do not provide all the inputs to each decision tree. So let's say for decision tree number 1, I will say I am not going to use credit rating. So decision tree 1 knows nothing about credit rating. Decision tree number 2 might not know anything about whether a person is student or not. So these decision trees are going to be different because you provide different amount of data to them. And this is very nice, yes? This is actually giving you some variability to this data. Now, of course, there are also some drawbacks, as you have now multiple decision trees to work with. Each decision tree has to have a lot of memory, and having many decision trees are going to require even more memory. Now, again, it's not well used for imbalanced data when you have some more certain classes than other. A lot of computations. It's no longer visually interpretable as it was for decision tree, because you would have to draw a lot of decision trees, and it's difficult to confuse in that amount. It might need to fine-tune certain parameters. It's not like straight away specifying, oh, you might need to work around with it, but it's also very fast to train, somewhat slow to make predictions. Again, if we go to the Python and see how we can use that, you can see that we import from sklearn ensemble random forest classifier. Here you specify in brackets how many decision trees do you want to use. So I say, for example, I will use 10 decision trees. Yes. Then you feed the training data and predict the testing data. So exactly same. All that has changed is my model. Yes, well, that is what I have replaced. So I could have basically specified here, instead of CLF, this random forest classifier, RFS, yes, and this part of code would work exactly the same. However, what we will notice is that now your accuracy, well, didn't go much better, yes, so it's even actually worse now, 72%. But this might be just not very well suitable problem for it, or you need to have much more estimators, yes, because you have 400 inputs, 400 pixels, and I only use 10 estimators as to, let's say, well, like I have digits from 0 to 9, it's 10 possible classes, I say I will try 10 estimators, but maybe you need to have more. Also, your handwritten digits have some noise, which is unavoidable when you scan some images, which may also be a problem. And also here you can see some link, yes, about more information about this algorithm, how to use it, etc. in some web resource, which you can also study if you are interested. So here you can see some examples of problems which we can try to classify, such as emails, for example, if it's spam or not, image classification, which I showed you just now. Yes, it actually works. It's not producing high accuracy, 72%, but it definitely works and predicts majority of the digits. It can be used in medicine for diagnosis, for classification problems. Now, for regression problems, you can predict some kind of price, predict what is expected demand for your possible product, yes, predict energy consumption or air pollution caused by your energy consumption, and so on. And the idea is very simple. You create something called ensemble learning algorithm. Ensemble learning algorithm means that you have multiple models and you stack them together into one big hypermodel, you can say so, yes. And here you can also, since for each decision tree we don't specify all data possible, only some parts of data, yes, you can study how important may be certain features, certain inputs. So for example, in our problem here, how important it is the income level for this kind of problem, or the fact that it is a student, because, well, student is going to need a computer for his studies, for his leisure, yes, and he is more likely to buy one, even if his income is not so high, yes. So that can help to analyze the importance of these features. Now, if we summarize this in the form of a table to compare decision tree versus random forest, now decision tree is a single model algorithm, it's just one tree, and a random forest is an ensemble model consisting of multiple simpler models. Now, decision tree has high bias and variation, but is tending to overfit data, whereas random forest, thanks to the fact that you skip some data points, yes, actually reduces overfitting. So you can think of this as also as a way to perform regularization. Now, decision tree is very good for visualization when you need to show how exactly your data set is organized, whereas random forest is very nice for efficiency, to calculate it in parallel for all decision trees at the same time. Now, noise is really problem for the decision tree and not so much problem for random forest. Now, decision tree has certain priorities for each inputs. Yes, as we have seen here, you calculate some entropy, you calculate information amount for each input, for each column of the data. So it prioritizes them. Yes, and in fact, you can see that here we have selected H as this first column, and as the second column, probably we should choose the next most informative column, which is if the person is student or not. Yes. Now the random forest has random inputs. Yes. So it may say, okay, I'm not going to use the fact that this is a student for this decision tree, and for the next decision tree, I'm not going to use his income level and whatever else and whatever else. So it doesn't use all the inputs. Now, decision tree can be unstable, and the random forest, although it consists of decision trees, multiple decision trees, but having many of them actually makes this algorithm more stable and more robust. Yes. Now here, if you are interested to see more details, you are most welcome to watch this link. Yes, how exactly this decision tree can work. But I'm going to stop here very briefly to say that each of these decision trees is organized somewhat differently. So, for example, tree 1 has as a first root parameter diameter of your fruit. So if it is more or less than certain value. Decision tree as the first input takes the color of your fruit, yes, so if it's red or orange. And decision 3 says if the diameter is specifically 1. So you can think of this as this is more intended to decide whether it is, well, small or large fruit, this whether it is red or orange fruit, and this again is very similar to the first decision tree, but now you can see that here, based on the output of the first case, where is diameter, the size, yes, so you can see that this part and this part are exactly same, because cherry is a small fruit and it falls either way into the, well, true or false. The label is different here, but the next step is we decide whether the color is orange, false or true, and for decision 3 we decide whether it grows in summer. Yes, so the condition is different here, and here is decide its shape and color. So that makes 3 predictions: orange, cherry, orange, and by using the voting algorithm, we decide that majority votes for orange, so that is going to be predicted as orange. Okay, so the next algorithm is support vector machine. Now, support vector machine is a nice algorithm which can linearly separate your data points. Yes, so here you can see some class 1 data points, green circles, and class 2 data points, red squares, which can be separated by a line in 2 dimensions, the plane in 3 dimensions, or hyperplane in more than 3 dimensions. Yes. So this is very similar to linear regression algorithms. However, not always it's possible to find this kind of a hyperplane, this separation line for this dataset you have specified. Yes, so I will maybe not delve too much into the details how exactly it works. Yes, but it well basically calculates the distance of each point towards this hyperplane. What we have here as the problem is that, let's say for example you have this data set originally, yes, where you can see there is no straight line that can separate the blue circles from red circles. Yes, there just is no such straight line that accurately can do. The line is complex shape. This is the case of two dimensions. So the support vector machine says, okay, let me add another dimension. So I convert this picture from 2 dimensions into 3 dimensions, and now it can construct the hyperplane that separates them linearly. Yes, as this kind of a section, dissection of this cube. Yes, so you convert this plane, the paper sheet, into some cube, and inside of this cube now this data is now separatable. If it's not separatable in 3 dimensions, you add the 4th dimensions, the 5th dimensions, until it becomes separatable. Yes, so this trick is adding this kernel function. Yes, so this kernel function is this kind of a map that converts this from 2 dimensions into 3 dimensions, from 3 dimensions into 4 dimensions, and so on, until you can linearly separate them. And that's what exactly support vector machine algorithm actually does. Yes, it converts your data into more dimensions. So say you have the data set with 5 table inputs, which cannot be linearly separated, so support vector machine is going to convert them into 10 inputs instead, which will be possible to separate linearly. Yes. Now, this can be also used in real-world applications for classification of text and documents, handwritten digits recognition, speech recognition, image classification, authentication, biometric identification, and other different stuff. So again, I provide you some example if you are interested to study, an article which you can see. Not exactly sure. This is certain map, yes, some area, and for this area they were, well, let's check it. What was that actually? Predicting some, I'm not sure exactly which, coverage of the certain map, yes? Okay, so it says here that it actually excels at image classification and handwritten recognition. So let's see in my Python example how well it does for our data set compared to random forest decision tree. I have also created a support vector machine classifier, SVMC, with a linear kernel, meaning that I am going to create the hyperplane that is linear, yes, some kind of a section of the space, or straight line, or plane, or hyperplane in more dimensions than 3, which is one of the cases, linear. Of course, we can use also non-linear. Again, I specify here the fit algorithm to train not neural network, but support vector machine, and then I make prediction on testing data set. And as you can see now, the accuracy is 92%, which actually works quite well. Yes, and I didn't do any fine-tuning here. I can specify some more parameters if I want to. Yes, I can maybe use non-linear kernel. It might show better results. Yes, but even so, this actually produces quite nice result. It's not a neural network even. Yes, it's support vector machine, which is very similar to a regression problem, which is more simple. Yes. So indeed it does well in prediction of handwritten algorithms. And as you can see, all of these algorithms are literally the same pieces of code. Yes, I only change this method here which I use, random forest classifier, support vector machine, or decision tree classifier, and majorly the program remains the same, again, which is nice and convenient, allowing you to play around and check whichever algorithm is better for you. You can also use neural networks of different types, maybe convolutional neural network, maybe recurrent neural network as well. Yes, so that's not a big problem. Now again, we can speak of some advantages and disadvantages. Yes. Now the main advantage of this algorithm is that it actually tends to search for the global optimum. Yes. Now, what does that mean? Well, let's make some very simple example of cost function. Yes, so let's say you have some cost function depending on your certain parameter theta, yes, and your cost function changes somehow like this. So what we can see here, some local minimums is here, some local minimum is, well, let me choose another color. So some local minimum is here, some local minimum is also here and here, but here we can see that actually absolute minimum, yes, and support vector machine algorithm is tending to search more for this global minimum rather than specific local minimum, because the gradient descent algorithm works like it's moving around this minimum, and in case it happens to be around this minimum, it's going to find you as solution this one, yes, and it will not even try to go further. Now support vector machine actually tries to find this global minimum, which is good, yes, for us. Now we can use different kind of kernels. As I said, kernel is this mapping procedure when you convert your lower dimensional input space into higher dimensional input space. And there are multiple ways to do so. It can be linear, it can be polynomial, it can be Gaussian, yes, from the normal distribution, making the bubbles around each of these classifiers. And accordingly, this can affect your accuracy in a large way. Now, it's also quite efficient, especially if you have not so much data and a lot of inputs. So let's say each of your picture consisting of millions of pixels, yes, and you only have, let's say, 100 of these pictures, yes, so you have million of inputs in your algorithm and only, well, 100 or so of different kinds of pictures. So in this case, it also tends to work quite well. Now, it also uses some fraction of data for training, so it splits the data set actually into training and testing parts, well, in training parts itself, without you having to do this, yes, which also is nice in a sense of regularization and overfitting, yes. Now, the disadvantages is that mainly it's very computationally intensive, yes, so that means it takes a long time to train, it works better if you have smaller data set which are connected, yes. It also, the problem is that if you recall, yes, we have logistic regression, we have neural network, and it predicts what is the probability that the picture I see is 1. What is the probability of this picture of 2? Now, this algorithm does not tell you these probabilities, it outputs you plainly the answer, the class 1, class 2, without any room for doubts left for you, yes? Now, it may need additional regularization for avoiding overfitting, and also very high sensitivity to noise, yes? So if your pictures are noisy, yes, this might work much, much worse. And also it is very limited to some binary classification problems, but again, it's possible to use this approach one versus all, as we did in the logistic regression, to convert binary, non-binary problems into series of binary problems. So, as you have seen here, it worked well for non-binary problems, yes, like here, yes, you specify this data set of handwritten digits, and it worked quite well. Because you can convert non-binary problem into series of binary problems, yes. Again, here is some additional material if you're interested to see how it exactly works, what this kind of margin is, because, well, it's not as simple as simply plotting this line. It also produces some extra space around this line, yes, and takes that into consideration. Now, let's also discuss about some, that is a weird slide, I believe there should be some picture, but okay. Some performance metrics. So how exactly can we tell if the algorithm is better or not? So here, for example, we said, okay, accuracy of the algorithm is 0.92, 0.72, and 0.77. From this, we conclude that the support vector machine of these three algorithms in these configurations yes, was actually the most accurate. And in this particular case, it will probably be true, yes, because we have like 5,000 pictures in total, and each picture 0, 1, 2, etc. is around 1/10 part of the total amount. So that means you have 500 pictures of zeros, 500 pictures of ones, 500 pictures of twos, and so on. Each picture is represented by equal amount of data, which is called balanced data set. So you have some balance, and there is no such problem. Now, sometimes you have not exactly balanced data set, yes, so let me remind you that the accuracy which we have seen there can be evaluated as the number of correct predictions versus the number of total predictions. This is in a sense integral measure which does not tell you how well it predicts specifically pictures of 0 or specifically pictures of ones, and as you know, for that we can construct confusion matrix, yes, to see these details. But accuracy is more like general average score for this entire model. Now, it works well, as I said, if data is well balanced. For example, you have 1,000 pictures of dogs and 1,000 pictures of cats. So in this case, let's consider non-balanced data set, when you have actually 999 pictures of dogs and only one picture of cat. So this is unbalanced data set, yes. You have way less pictures of cats, which can lead to overfitting. So let's say, for example, we create a support vector machine algorithm, we train it, it happens to have overfitting, and what it is going to do in this particular situation is simply overstate that the picture you have shown me is a picture of dog. But did you look at that picture? No, I know for certain that it has to be a dog, yes? But maybe you will, check out this picture and see if it's actually dog or cat. No, it doesn't matter, yes? So what it does, it says that this is a picture of dog, regardless of what is shown in this picture, because of this overfitting. Just because the cat is so low probability event that it doesn't bother to make this prediction. So actually, you can even program it like this, that you say you send some picture to the algorithm, then normally it should run some model, which then does if something, then it is a dog, else it is cat, some type of this normal algorithm. However, what we got as a model is that model is going to say that it is always a dog. So it doesn't actually predict anything, it simply states the picture is dog. Yes, that is basically all the algorithm does. And surprisingly, for this case of the algorithm, the accuracy is going to be 0.999, which is remarkable, very good accuracy. It made one mistake, so what about it? Yes, for our data set. The problem is that this was testing data set, a training data set. And when you will deploy this model in some real world applications, people will start showing pictures of their cats to this algorithm, and it will fail to predict this as a picture of cat. And the real accuracy in testing data set will be much worse. Yes? So this has happened because of the poor balance between data set, because, well, it's not a good way to train an algorithm anyway, yes? You should actually provide as many pictures of cats as possible to get a good and reliable result. However, this clearly shows the problem with the accuracy metric, because this algorithm is horrible, it's bad, but the accuracy states that it's remarkable. Yes, so that means that the accuracy is not always the best way to tell if your algorithm is doing well or not. So if we make the confusion matrix of this case, you will see that we have failed to predict cat when it was actually cat. So here we have 0 of the correct cat predictions, which is a false positive for dog. Yes, so it was cat, but it predicted as a dog. So that means it's not a dog actually, but was predicted as a dog. So that is a false positive, yes, here. And false negatives for dogs were not happening, yes, because there was no such situation when there was a picture of dog and it said this was a picture of cat. Yes, so you can think this as a test result for some COVID, false positive, false negative, yes, exactly the same way, but instead of test for COVID, we make test for if it's dog or not. Now, from this confusion matrix, we can specify additional metrics called, for example, precision. And precision is totally different stuff from the accuracy. Yes, mainly because now you can also, well, you could calculate accuracy for each of these class separately too, not a problem, but precision is a little bit special, yes? So what we answer as a question here is how much of your dog predictions were actually correct. Yes, so we don't really care about how many predictions of dog it made, but more like how accurate it was in its predictions. Yes, so if it says that it is dog, was that really a dog? That is the question. The precision answers. Yes, and it doesn't answer how many pictures of dog it was able to find. Yes, so basically we here worry more about quality of prediction, not quantity of prediction. Yes. And there is another metric called recall, which does opposite, which says what proportion of actual positives was discovered. So how many pictures of dog was it able to find? And here we care more about quantity rather than quality, yes? Now, as you imagine, these two are actually conflicting with each other. You cannot have high recall and high precision. If you increase some requirements in your algorithm, it's going to produce higher precision, but your recall is going to drop because of that. You can think of this as a false alarm detection in some computer network when you want to find some intrusion, yes? Well, in that situation, it matters much, much more to actually, that you do not skip this attack, yes? So even if it's false alarm, it's better to raise false alarm than to fail to detect a possible intrusion, yes? So in this case, we can say that recall is more important parameter because, well, we don't really want to have any chance of skipping the alarm, yes? That was happening. Now, in other cases, such as, let's say, medical diagnostics, yes, we really want to be sure that person is infected before we want to do something to him, yes? So precision is more important parameter in that case, yes? Now, actually, as I said, they tend to conflict with each other, and when you try to improve one parameter, you basically get another parameter worse. But if we return to our case with cat and dog's picture classification of this particular data set, then we will see that precision and recall for this data set, for this problem, for this model is 0. Yes, which shows that it's actually not as good classifier as accuracy stays, yes, because precision and recall says otherwise. So now if you calculate accuracy, precision and recall, you will have more complete picture of what happens, yes? And what you can do to improve situation is probably add more data in this situation, because having only one picture of cat is very, very low statistics, yes? We need to have much more. Now, as I said, precision focuses more on relevancy, the quality of predictions, whereas recall focuses more on the quantity of this prediction, how many cases you were actually able to catch. Yes. Now there is also a combined metric called F1 score, which is nothing else than harmonic average, yes, which came from geometric average versus arithmetic average, combining these two metrics together. Yes, so sometimes F1 score can be used instead of these precision and recall metrics when you cannot decide which one is more important for you. Then you want to find the optimum distribution between both of them, and you can use F1 score for that situation. But that is not all. These metrics are somewhat also limited in a sense that you make prediction for a certain assumption and only that. There is even more universal metric called receiver operating characteristic, ROC curve. Now, it's called this weird name, yes, related maybe to some radars and stuff like that, just historically because of that. Because, well, what happened historically before was that we were having some radars, yes, some screen for radar, something happens here, and then you see some dot as the flying airplane or something else, yes, on this radar. And the question was that actual airplane or that was a false alarm, yes? So, and it depended a lot on your threshold. So if you recall, so let's say we have some logistic regression problem, predicting if the target is airplane or not, yes? So logistic regression, neural network, decision trees maybe also, yes, other algorithms, they all don't specifically say yes or no. What they do is give you the probability that this is airplane with a probability, let's say 0.75, and then it is up to you to decide if that is considered to be airplane or not. Of course, mistakes might happen, yes, but if we compare with a threshold of 0.5, we are quite certain that this is airplane, yes, because it's very well above the 0.5. However, we can change this threshold, yes, and specifically for this threshold 0.5, you will see on this ROC curve this as only 1 point, yes, so this is for the decision threshold 0.5, single point on this line. Now you will say, okay, this is actually very important and I don't want to miss any possible aircraft. So I'm making this threshold somewhat stricter. Yes, so now I'm going to say, okay, now my threshold is going to be 0.25, which of course will lead to the situation that it will report this as an airplane more often than it actually is. Yes, so it will produce some false alarms, but it will also guarantee that you are not going to miss this airplane, yes? Yes, you will sometimes have false alarms, maybe more often than you want to, but at the same time, when actual airplane will be there, it will also report it as well, yes? So this will produce a next point. Well, actually, it's in opposite direction, 0.25 in this direction. Or you could say, okay, it's not so important, yes, well, maybe not for this particular problem, of course, but maybe some, I don't know, which kind of problem. Let's say for medical analysis, yes, we really want to be sure that it is actually some disease rather than, well, again, it depends. So if it is some emergency about some epidemic, then we don't want to rule out any possible case. But if we speak about treatment of specific person, then of course we want to be extra sure that it's actually this is the case. Yes. So in that case, we can increase this threshold to 0.75. Yes. For example, to be extra sure, which will produce this point. So what ROC curve does, it changes this threshold and analyzes how true positive rate is versus false positive rate, yes? And constructs this as a certain line. Now you can see this is just for one algorithm. So let's say, I don't know, let's say support vector machine. Now for another algorithm, you are going to do the same stuff. You are going to train some neural networks and make another line which might look, let's say, somehow like this. And for logistic regression, it maybe is much worse, something like this, etc. Yeah? So basically, the perfect line would look like a square, like this. That's what we want to get. So we want to get this point, this edge, as close to this corner as possible. That is the ideal ROC curve, yes? And this ROC curve shows you how often it will produce false alarm versus the possibility of not detecting when act actually happened. So depending on your situation, what is more important for you to not to lose this airplane when it actually was there, you may say, okay, I'm more interested in this true positive rate, yes, to have as high as possible. So you focus on this one. And that means that you are going to choose threshold of, let's say, 0.1 to be extra sure that whenever there is even slightest suspicion of this to be airplane, it will report to you that something has happened, yes? And vice versa, when you are considering some dangerous operation maybe or something else, you want to be extra sure that it's really worth the risk, yes? So you make this threshold much higher, let's say 0.9, to rule out any false analysis results. You repeat some analysis and all that stuff, yes? So this ROC curve provides you the way to choose what is more important, false positive or true positive, yes? Now, as I said, we can compare different algorithms by their ROC curves, but also there is a way to do that by calculating the area under this ROC curve. So if you calculate this area beneath this ROC curve, then you are going to get just one single number, which is more convenient to compare than having multiple pictures, multiple curves, yes, and trying to decide, okay, which one I'm going to use because there are so many of them. Actually, let me open some other link for you, which I have provided you some additional explanation here. Yes. So what you can see here is distribution of the spam email and not spam email and our threshold of 0.5. So when it says that the message is spam email with probability 0.75, it is up to us to decide whether it is really spam or not. But there will always be probability that we make mistake, because some messages that were very similar to spam were not recognized as spam, and vice versa. Some messages that are not spam, but maybe because of some text that was used there, maybe because of product names or something, were recognized as a spam. Yes, so there is this overlap of these distributions. Now, if we specify this threshold at 0.5 in this example here, there will be always risk that you will skip some real spam message at the cost of reducing the situation that not spam message was marked with spam, yes? Now, if you say you make the threshold of 0.4, then you are basically guaranteed to filter out all spam messages, at least which were used in this training example, but it will also at the same time increase the chance that non-spam message will be marked as spam, yes? And vice versa. If you really care about not marking your email message as a spam, then you are going to choose a threshold of 0.6 when you compare with probability. This will exclude the situation that the spam message, non-spam message was recognized as a spam, but it will also reduce the number of images or messages correctly recognized as spam. So you will get actual spam more than at the decision tree of 0.5. Again, it's about the decisions, and what we can do here is maybe we can try to make another algorithm. Maybe we will use not support vector machine but neural network instead, which will produce smaller overlap for this situation, yes? So now there was some animation here. Yes, it's here. You can see here how this area ROC curve is constructed depending on how much these distributions overlap. So if they overlap a lot, then that's bad ROC, and the better the algorithm we have, the less is overlap between these false positive, the yes and no predictions, yes, and the more this area under curve increases to 1, yes. So basically, this area under this curve is single number, and the higher is this number, the better is your model. Yes, so perfectly it should be 1, yes, but as you can see, it changes depending on how good is your model. And this overlapping depends entirely on your algorithm, on your model which you have trained. Was that support vector machine, or random forest, or neural network? And only then, when you have these pictured, yes, you can decide what kind of a threshold do you want to use. Yes, so now let's say we have this result of distributions for our positive, that is yes, spam message, and negative, not spam message. They overlap somewhat. You can improve that by training another algorithm, but for this specific algorithm, you have to decide which threshold are you going to use. So the average one, and most commonly one, will be 0.5. And that's what we used in our practical exercises and also. But as I said, you might want to consider other thresholds, which are simply going to move you on this line. Where are you exactly right now? So for the 0.5 threshold, we are here. For another threshold, we'll be here or here, depending what is more important for you. And this line can help you to decide what is important for you. What is important for you, whether you want to have less actual spam messages, or it's more important for you not to miss some important message because it was falsely marked as spam. Yes, so you can either decide the golden, well, middle point, which is 0.5, or change this into any favor. Yes, and this line basically shows you this dependency between these two. Yes, it doesn't specifically say that threshold 0.5 is somewhere around here. You have to calculate it still somehow. But anyway, if you want to compare different algorithms, yes, like good model, bad model, then you can use this area under curve as a single number to make a final decision. Which algorithm are you going to use? Of course, with higher area under curve. Okay. So this concludes today's lecture. If you have any questions, don't hesitate to ask. But before we finish, I also wanted to maybe give more information about the grading, about how much practical exercise we have, how much practical exercises we are going to have next weeks, yes, and how I will be grading you. So first of all, I try to contact about deadlines. The official deadline for exams and all that stuff is still not out there, but the deadline for putting all the grades, they said that you know it, is January 24. Yes, so that is the final deadline when you need to submit all your practical exercises for machine learning. Now, because I'm not putting the grades from probability theory, and probability theory is going to be 1 week less, more or less, yes, for me to be able to give these grades to that person who is going to put them. And, well, because you have lectures, you have tests there, you have practical exercises from me, and these two grades need to be combined somehow, yes? So let's say that for probability theory, again, if you will send it 18th or 19th, it won't be much problem, yes, but try to stick to this schedule, that this is a deadline for probability theory, and this is the deadline for machine learning practical exercise. If there will be some more accurate information, I will try to give it, but basically it's the middle of January either way is the deadline for all the practical exercises that you need to submit in the system, yes? So we will have a total of, I believe, let's check it, 6, that seems, yes, practical exercises here. Yes, so we will have 6 practical exercises in machine learning and 6 practical exercises in probability theory also. However, there is one thing here I'd like you to notice is that the practical exercise number 3, this neural network training for multi-class problem, is actually worth more than others. Yes, so if we go here, where was that? I don't think. It's grades. Yes. It doesn't says here anything. But anyway, so I mark each practical exercises in a range from 0 to 10. 0. Sorry, they are in different order here, 0 to 10, 0 to 10, and for the practical exercise number 3, it's marked from 0 to 20. So actually it's worth like 2 practical exercises, yes, because of its complexity. Now, it's up to you to completely to decide which you want to submit, because I realize that some of them are very difficult, yes. Even if you do it partially, still don't hesitate to submit whatever you have. Maybe you won't get 20 points, maybe you will get 10 points, and it's still plus point for your grade, yes. Maybe it's easier for you to give practical exercises 5, 6, and 7. It's okay. You don't have to be starting from 1 and all the way. Whichever you can do, send everything that you can, yes? And then you need to have minimum of 3 practical exercises, again, considering that this one counts as 2 practical exercises, yes, to get a positive grade, just to pass the course, yes? And the more you have, the better is quality of your reports, the better the grade goes, all the way up to 9. Now, to get the maximum grade of 10, I'm not yet exactly decided how to do it, but probably at the end of the course I will include some bonus task, yes? Which is not a mandatory practical exercise. If you feel like you want to try to do it, you can try to do it to get a better grade. And, well, not necessarily maybe 10, but it will be in such way that it will make more sense to do other practical exercises before this one, because, well, there you will have to do everything yourself, there will be no video record, no nothing, yes? So it's up to you to decide. But again, it's completely up to you to decide which practical exercises you want to do, in which order, and how much, yes? You can do all of them, but maybe by half, yes? If you feel that you cannot finish them. But again, don't worry, as I said, next practical exercises 5, 6, and 7 are going to be much simpler than the first ones, yes? And it's intentionally made, so. So that is for the machine learning, 3 practical exercises, yes? And for probability theory, basically it's the same. Also 3 practical exercises to get a positive grading, and the more you have, the more you can get all the way up to the 10. There will be no bonus task in the probability theory because you have some tests, probably even exam, I'm not sure, about another instructor, not me, yes? So he will decide that. And for the deadline, as I said, once I will have exact deadline, but at least I was told that it's 24 to put on the grades. Just practical exercise. Well, because they are quite complex. They are quite complex and you have to spend a lot of time for that. So I believe it matters more how you work during the entire semester rather than whether you were lucky on an exam to pick the correct ticket or not. Yes, so that makes more sense for me. Okay. So are there any questions more? So thank you then for today, and see you next week. Some of you will have practical exercise today. So okay, thank you.